Assalamualaikum and hi, my name is Nurfarina Fatin binti Abdul Muttalib with matrix number of BS23110407. So for today, I'm going to explain on solving diffusion of heat equation using a technique called separation of variables. So I'm going to put the equation right beside here because I've already written the solution in this gadget. So as you can see, the PDA problem right beside me, these two are the boundary condition, this one, and this is the initial condition in which the function u at time 0 is some arbitrary function of x. Note that in this PDE problem, both the differential equation and the boundary condition are linear and homogeneous. Next, in separation variable, assuming that the function can be separated into a product of two functions, then it can be simply write each of these individual solutions using a subscript as an index. So the most general solution can come up with is u equals the sum from n equals 1 to infinity of an times x sub n of x times t sub n of t, where the an are the coefficient. Then we need to substitute the separable solution into the PDE. Differentiate u respect to t. Then the function capital X only contains terms in small x. So for the partial derivative of time, we can just treat it as constant. So the derivative of u with respect to t is just capital X times the time of capital T. And then moving on, same logic can be applied to the second partial derivative of u with respect to x. Then we end up with t times the second derivative of capital with small x. And then plug this into the PDE, then we'll get something like this in this green circle over here. So effectively, by dividing both sides by capital T, we get this one. And then, so right now, let us start now by choosing a positive constant. We can write the constant as lambda squared, then the separation equation will become like this in this red circle thingy. Then we can break it up. We can break the expression into two separate ordinary differential equation, one in terms of t and the other are in terms of x. Then we arrange the equation in t, and then rearrange the equation of x. We'll get something like this. And then we can write down the u as a times the exponential as we let the time approach infinity. The solution blows up if b and c are both 0. So this doesn't make sense. So right now let us see the second case, which is the constant equals to 0. And then the separate differential will become like this. Then once again, the equation we can break up the equation into two expressions. One is this and one is this. And then we can write the u down as a time bx plus c. So let us use this boundary condition in the expression for u to find its constant at x equals 0 and x equals L. But since a and b equals to 0, we can conclude that the whole function is just 0. Then we can set the lambda constant is equals to 0. So that's all from me. Thank you.